Hello, my name is John Cerebes, and this is my Lab 4 report on oscillations. In this lab, I analyzed a mass oscillating on a spring in 2 dimensions, swinging side to side while also bouncing vertically. I tracked the real motion using video analysis, built a computational model to predict that same motion from fundamental principles, and then use the model to test whether the energy principle is satisfied. The goal of this lab has two halves. The first half, I used Tracker to record the x and y position of the mass frame by frame and exported that data to a CSV file. For the second model, I built a GlowScript program that predicts the motion using only the momentum principle and the forces acting on the mass. Then I compared the two and checked the energy. As a quick preview of the results, the model matched observations closely in both directions. The total energy stayed at 0 throughout, and interestingly, the x and y oscillation periods came out a little bit different. 1.65 and 1.5 seconds, that's a little bit different. We'll talk about that later. So looking at it now, here are the physics equations the model is built on that are going to be used in this lab. The momentum principle, Newton's second law, which is Newton's second law, gives us the update equations. Each time step, the net force updates the velocity, and then the velocity updates the position. There are two forces on mass. Gravity always points straight down, with magnitude being mass times gravity. The spring force is an interesting one. It's negative k dot product s dot product l, or l hat, which is direction. That direction matters as the mass swings. The spring force allows it. Direction matters because as the mass swings, the spring force allows it to. That one line of physics is what makes two-dimensional motion work. For energy, I chose my system to be the spring, the mass, and the earth. That means nothing in the surroundings does any work on the system, so the energy principle detects the delta E, the sum of the kinetic, gravitational, and spring energy, which is going to be 0. So now for the experiment, I analyzed the video in Tracker. I calibrated distances using the calibration stick and placed the origin at the spring's attachment point. I marked the positions on the mass every frame, about 70 frames, covering 6.5 seconds of motion at 10.53 frames per second. System values were a mass of 0.402 kilograms, a spring constant of 6.86 meters per second, and a relaxed length of 12.5 centimeters. My initial position came straight from the first row of data, about negative 0.109 in x and negative 0.64 in the y, and the initial position was 0 because I started tracking right when it started moving. So here is the most important parts of my computational model. So every iteration, the code recomputes the spring vector L from the current position, gets the stretch by subtracting the relaxed length, and calculates the two forces. Gravity and the spring force along L hat. That's what happens. And then it adds them for the net force, uses the momentum principle to update the velocity, and uses the velocity to re-update the positions. And then it recomputes the four engines: kinetic, gravitational potential, spring potential, and then their total. One important detail is that my time step is 1/200th of a second. That's 20 model steps for every frame, so small enough to keep the force update accurate. So now the results. In these plots, blue is the model's prediction and red is the actual tracker data. In the x direction, the match is nearly exact. In the y direction, the shape and timing match, but you can see the model's amplitude is slightly larger than the real data. That makes sense. The real system loses a little bit of energy to air resistance and friction inside the spring. The model doesn't include any of that. It's a perfectly lossless system. So here are the energy changes over time. The red and green curves, gravitational and spring potential energy, mirror each other, trading energy back and forth. The blue is the kinetic energy oscillating with small amplitude, and the orange curve is the change in total energy. It stays flat at 0 the entire run. So the first question discussed is the energy principle satisfied, and that's going to be yes, because the system includes the spring, the mass, and the earth. No external work is done, so that change should be 0. That's exactly what the model shows. Individual energies swing by about 1/10 of a joule, but at every instant they cancel. Energy is transformed between forms, which means it's never created or destroyed. So the second question is the oscillation periods from the peaks of my data. I measured a period about 1.65 from the y, and then about 1.65 from the x, and then 1.5 from the y. They're different because the two directions are governed by different physics. The y motion is a spring oscillation whose period depends on the mass spring constant, while the x is pendulum-like. swinging, whose period depends on the hanging length and gravity. There's no reason for these to match, and small effects like drag and tracking precision add to the difference. Finally, source of error, manual tracking, calibration precision, and drag. My model leaves out, which is why that's going to be a visible amplitude gap on the Y. Overall, a model built from nothing but the momentum principle and 2 reproduce dimensional forces, conserve energy exactly. Thank you.